Hi, so I'm Marc-Olivier from ICFO Barcelona, from the QIP group, and this is a presentation for the conference AQIS 2020. So I would like first to thank all the organizers of this online conference. So today I will present how one can obtain network non-locality from the token counting and the color matching strategies, which are, as I will show, rigid in many networks. So this is inspired from this work, which is a joint work with Salman and Beigi. So first, before discussing network non-locality, I want to introduce it using standard Bell non-locality. So in standard Bell non-locality, we study scenarios like this one, where there is one source shared between two parties, and those two parties have inputs, measure the state depending on their input, and obtain an output. And there are two main ways to describe this kind of scenario. The first one is to use the classical local way. Here we assume that the source is a classical local source of randomness and that the output A is just a probabilistic function of X and lambda. And then, given this source of randomness and those two functions, one can compute the probability of saying A, B, knowing X, Y. So this is what I will call a classical explanation for the correlation. And then there is a second explanation, which is a quantum explanation in which we have a quantum source and two quantum measurements for Alice and Bob. And again, there is a formula to give the probability of A, B knowing X, Y. And the main result of Bell non-locality is that there exists an experiment, which is the CHSH experiment, in which you have this state and those measurements, where when we look at the probability of A, B knowing X, Y, we obtain a very special probability distribution I call PCHSH, which is of course quantum, but which is non-local. So there is no classical way to simulate this quantum probability distribution. So now I will go to network non-locality. So in network non-locality, and here I have a specific network, which is the triangle network, you consider several independent sources, so 3 in this case, and several parties measuring those sources. So here, for instance, Alice will measure this source and that source. And then she will obtain an output. And again, we are interested in the probability distribution of A, B, C. Again, there are two different explanations. The first one is a classical explanation in which I have classical source of randomness and probabilistic function A of beta, gamma, etc. And I have a way to compute the probability distribution given the source and the output functions. I can do the same with quantum models. So now I assume that I have quantum sources, quantum measurements, and I ask what is the possible probability distribution. And here in network non-locality, the main question we ask is, can we find examples of quantum experiment giving quantum probability distribution which cannot be explained with any local model? So I want a precise quantum experiment such that there is no way to simulate classically this probability distribution. And actually, this is a very difficult question. So, of course, this is much more general. I can do this in any network. So I presented the triangle network, but in this kind of network, you can also define classical and quantum strategies and ask the same question. Before explaining how token counting can help to answer this question, I want to go back a bit to the motivation. So there is a theoretical motivation first, which is that this gives a deeper understanding of quantum correlation. So actually, Bell non-locality, Bell standard non-locality is just a very precise case of this network non-locality framework. And if we want to understand why quantum correlation are very different from classical correlation, we should also understand this in networks. And there is a second motivation, which is more practical, which is about the quantum internet. So we believe one day that we will have a quantum internet. And in this case, Several independent sources will be shared by several parties. Actually, we'll have a lot of sources and a lot of parties. And if we want to study non-locality in this quantum internet, we have to go to network non-locality. So now I will explain what are token counting strategies. And I will consider only the simplest token counting strategy I can imagine, which is in the triangle with one token per source. So I will first describe classical token counting strategy with one token in the triangle, and then I will explain quantum one token strategy. So with classical strategy, I first consider the source, and I will just say that each source has one token to distribute. And it will distribute it either to the left party or to the right party with probability 1/2. So for instance, in this case, beta distributed to Charlie and alpha distributed to Bob. So to the left party and gamma to the right party, Bob also. So this is for the source. I can use also a quantum description for this classical state, which is given there. So now I consider the measurements, and in a token counting strategy, the party should measure the total number of tokens they received. So here, in this case, you see that Bob received 2 tokens, so he has to output 2. Charlie received 1, he outputs 1, and Alice received 0, she outputs 0. And this corresponds to this measurement. So again, this is a classical measurement, but I use a quantum description. And I may have different cases, so I can also have this case in which they all see 1 token. And then once the party have measured how many tokens they received, they are also able to measure additional degrees of freedom. And one very important degree of freedom is, when I had 1 token, where is this token coming from? So here, for instance, Charlie had 1 token, and he can additionally measure where the token is coming from. And in this case, he finds that it comes from the left. So now let me explain what are quantum token strategies in this triangle with 1 token. So here again, the source will distribute 1 token, but now they may do it in superposition. So for instance, the source will distribute the token to the left and to the right. So now this state is, of course, not classical anymore. And the party will also measure the total number of tokens. So the way I write the measure is exactly the same. So you see that I can have, again, different cases. So for instance, Bob might find 2 tokens, Charlie 1, Alice 0, in which case I know that the token of gamma went to Bob. Or they might also find 1 token each, in which case I cannot say where the tokens are coming from. And then once they have measured how many tokens they saw, they may also measure additional degrees of freedom. For instance, they may measure the degree of freedom where the token was coming from when they saw 1 token. And as they are doing now quantum measurements, they may measure this in superposition. So Charlie, for instance, may measure this state or that state in these spaces, in which case he will obtain information about where the token is coming from, but it's quantum information in superposition. So he will find that the token comes from a superposition of left and right. Okay, so in order to explain why quantum and classical token counting strategy are very different, I will go back to this specific case of 1 token per party. So I will post-select over the case where each party saw 1 token. And I will first consider classical token strategy. So in this case, you see that if all parties obtain 1 token, you have 2 choices. Either gamma went to Bob, alpha went to Charlie, and beta went to Alice, so the token turned into this direct way, or the token turned in the anti-direct way. So I have this classical state when I post-select over 1 token per party. But now if I consider quantum token counting strategy, it's totally different. So it's totally different because actually I will have a coherent superposition between those 2 cases. So the global state of the 3 sources after the post-selection of 1 token per source is this coherent mixture of turning the direct way and in the anti-direct way. And quite clearly, those two states are very different. So then let us imagine first that I have a quantum token counting strategy and I want to simulate this using a classical token counting strategy. It is quite clear that it will be hard because this state is much more complex than that state. So it's quite clear that I should obtain more correlation possibilities when I measure those additional degrees of freedom with the quantum state than with the classical state. And actually, this is the case, and this is what we prove in our paper. However, our goal here in network non-locality is totally different. What we want to do is we want to find a quantum token strategy such that it is not possible to simulate it using any classical strategy. And when I say any, I'm not talking only about token counting classical strategy. I'm really talking about any possible strategy in which the source do not distribute token anymore, but may distribute much more information, which is much more complex to describe. So this case is completely different, and a priori it's not clear at all that there is no way to classically simulate quantum token counting strategy. And here's where our main results come into play. So actually, what we were able to prove is that this is not a problem because we have rigidity of token counting strategy. So what we have proven is that if you consider any correlation, P, coming from either classical or a quantum token counting strategy, and if you consider any classical strategy S that simulates P, with this any expressing the whole complexity of possible classical strategy, then actually S must be a token counting strategy. So there is a unique way to classically simulate token counting strategy, which is to use classical token counting strategy. And when you know this theorem, it becomes clear that it is not easily possible to simulate quantum token counting strategy because you must, because of this theorem, use classical token counting strategy. And it is quite clear that then it is hard to simulate this using that. And this is what we explain in our paper, and I don't have time to go into the details. Instead of going into those details, I want to explain why this is actually much more general than just the triangle scenario. So you can now look at general token counting strategies, and first you can put more token in this triangle and you will have the same result. And you can also look at various networks. So if you look at a network which looks like this with many tokens for each source, we are able to prove the same theorem. So consider in this network with some given number of tokens for each source, a probability distribution coming from a token counting strategy. Consider a classical simulation of it. This classical simulation must be a token counting strategy. So this theorem is not valid in all networks. It is valid only in what we call no double common source networks. So this is precised in our manuscript. And in particular, it excludes this network. So this theorem gives a generic method to obtain non-locality. And using this generic method, we were able to prove non-locality in the triangle, in this network, and actually we give a very generic method which is able to work in many networks. So in the few minutes I have left, I also want to say that this token counting strategy and rigidity is not something which is just about token counting. So we were able to find another class of strategies which are also rigid, and this is column matching. So let me briefly introduce what are column matching strategies. So in column matching strategies, you have first So in this scenario, for instance, in this network, you have sources which will take different colors. So for instance, let's say yellow or red or purple, and they may take it in a classical way. So for instance, this source will have some probability to be yellow, some probability to be red, some probability to be purple, or also in a quantum superposed way of all the colors. And then the party will measure if all color match. So a party will measure if all the source he's connected to are of the same color, in which case he will output it. So for instance, in all those cases, Alice sees the two sources of the same color yellow and she has to output it. And she's the only party in this case. And then the party may measure additional degrees of freedom. So for instance, they may measure the color coherently. And in this case, we were also able to find a rigidity result. So actually, it's the same. If you consider some probability distribution correlations coming from a color matching strategy, and if you consider any classical simulation of this correlation, then this classical simulation must be a color matching strategy. So again, this theorem reduces a lot the class of possible classical explanation of your correlation, and it leads to network non-locality example. So again, this is not valid in all network. So for instance, this network is excluded, and you have to have a look to our paper to look precisely into this. With this, we were able to generalize our previous result with token counting. So in particular, we can prove non-locality in this network. In this network and its generalization to any n parties. And in many other networks, we also found a link to graph coloring. And in many networks where you have graph coloring, you can find non-locality, network non-locality using color matching strategies. So I am done with my small presentation, and I will be very happy to discuss this during the conference. See you.